In this second lesson, we're going to have a look at velocity time graphs, because last lesson we looked at displacement time graphs. Now, on a velocity time graph, we've obviously got velocity on the y-axis and time on the x-axis. And these are a bit more interesting. There's a few more things we can calculate from them. Now, on the displacement time graph we had before, we said the gradient was the velocity. So let's start off by looking at the gradient of the velocity time graph. Maybe let's look at this first section, section A, and find the gradient of it. So let's just draw on change in y and the change in x. So the change in y here is 30 meters per second. And the change in x is 2 seconds. So my gradient of my velocity time graph is 30 meters per second divided by 2 seconds. So that's going to be 15. Now look at the units. Meters per second divided by seconds again is going to be meters per second squared. So that's the acceleration. Okay. So the gradient of a VT graph gives you the acceleration. Or you can think of it as the rate of change of velocity is acceleration. Another property we can look at on these graphs is the area. So I'm going to look at that same area. I'm going to look at section A, this triangle here, which I'm not going to highlight in green. I'm going to find out what this area is that I've shaded in. To find an area, well, it's a triangle, so I can do half base times height. So that's half times 2 times 30. And again, let's look at the units. In fact, let's write in what the units are. So half times 2 seconds times 30 meters per second. So that's going to give me an answer of 30. Now let's look at the units. I've got seconds times meters per second. So that's m times m over, sorry, not m times, seconds times m over s. And you can see I'm just going to get meters. So the distance travelled in section A is 30 meters. So the area under a VT graph is equal to the distance travelled. Okay. So I could do that for any area. So if I wanted to look in section B, well, that's just a nice rectangle. Section C is a trapezium. Let's look at section C. I'm just going to do this in a different color. Okay, in section C, to find the distance, this shape is a trapezium. For a trapezium normally, if I was finding the area, if I call this side A and this side B, and this the height, it would be half A plus B times H. That's the formula for the area of a trapezium. Now here it is a trapezium, but it's sort of tilted on its side. So it's going to be half, well, one length is this length here, which is 30, plus the other length, which is here, which is 50, times the height, which is actually across the bottom here, which is 3. So then I can calculate my distance travelled in section C. So 30 plus 50 is 80, times 3, 240, divided by 2 is 120 meters. Okay, so we've got two facts here. On a VT graph, we can find the gradient, which gives us the acceleration, and we can find the area underneath it, which gives us the distance travelled. Okay, here's a slightly more interesting velocity time graph. There's quite a few different sections here. And we're just going to look through each section, decide what exactly is happening in each section. Let's divide them up. Okay, these are the different sections we're going to look at. So in the first section, bear in mind this is a velocity time graph, the gradient is constant. Okay, the gradient's constant, so therefore the rate of change of velocity is constant, so therefore the acceleration is constant. What else can we say about it? We could say it's a positive acceleration. It's increasing in speed. We could probably calculate it, couldn't we? We could do 4 divided by 5. So that's 0.8 meters per second squared. Okay. We could find the distance traveled. If I find this area in here, so that would be 4 times 5 divided by 2, which is 10. So that'd be 10 meters traveled in here. In the next section, so the second section looking at, well, it's flat. So the gradient is 0. So that means the rate of change of velocity is 0. So we've got a constant speed, or a constant velocity, which means that the acceleration is 0 meters per second squared. Okay, it's not changing. The area we could work out as just a rectangle. We've got, this is 5, 6, 7, this must be 8 here. So we've got just 4 times 3, so that's 12 meters traveled in here. This next section, this is interesting. I want to look at the whole section, and it goes through 0 meters per second, because remember this is velocity. So the first thing to observe is it's going downwards. So we've got a negative gradient in here. If we've got a negative gradient, that means we've got a negative acceleration, so it must be slowing down. We could call that decelerating. Okay, maybe let's calculate what that is. So it goes from 4 all the way down to -3. So that's a change of 7. In fact, it's a change of -7. In terms of time, it goes from 8 seconds to 15 seconds. So that's 7 seconds. So it's deceleration. So, well, it's decelerating at 1 meter per second squared, or we could say its acceleration is -1 meter per second squared. It's slowing down at a rate of 1 meter per second Now, this is an interesting point here, because this means that the velocity is 0. At this point, the velocity is positive, and at this point, the velocity is negative. So it's slowing down to the point where it's basically stopped, but it doesn't just stop and then wait. The velocity keeps decreasing. Well, you might think, well, what could be slower than being stopped? Well, because we're looking at velocity, it's a vector. So actually what's happening is it's starting to move backwards. So it's moving forward, but slower and slower and slower and slower until it stops. And then it starts to move in the opposite direction, is what's going on. And it gets faster, but moving in the opposite direction. So its velocity gets more negative. I'll show you what I mean by that. I've got a little simulation here, which is quite good. So I'm going to make this object move, and then I'm going to slow it down to the point where it stops, and then it's going to start moving backwards. Okay, so it's zooming off. Now I'm going to slow it down, and then it's eventually going to slow down and go backwards like that. Okay, we could do it the other way. All right, let's slow it down, and then eventually it's going to start to move the other direction. That's basically what's happening. Okay. Ooh, ooh. Okay. In this last section, between 15 and 20 seconds, it's a curve is the first thing to notice. So if it's a curve, that means the gradient is changing. Let's have a look at the gradient at some different points. If we took the gradient here, it's basically a flat line. Okay, so I'm drawing a tangent to help me find the gradient. Here, it would be more like this. And here, I think it's even steeper than that. So its gradient, maybe if I draw one in between as well, is starting low and getting steeper. So the gradient is increasing. Remember, the gradient of a VT graph is your acceleration. So that means the acceleration is increasing. So it's not just getting faster, but it's getting faster at a faster and faster rate. Okay. So its rate of change is increasing and getting steeper and steeper. We could try and estimate the acceleration by finding the gradient of these tangents. You could draw on a tangent by hand and you could find the gradient of it. If we were going to try and find the area here, then we would have to try and come up with an estimate. Perhaps you could split this area up into some rectangles or up into some trapeziums and estimate it. But because it's a curve, it's never going to be quite accurate here. Speaking of the area, notice that the area here would be positive, and then when it starts moving backwards, well, its displacement is going to decrease, so we could actually consider this area here to be a negative area because it's below the axis. Because it's no longer moving away from the origin, it's now moving back towards where it started, so your displacement is now decreasing. So you can have a negative area there if you're talking about displacement. So lots of things to think about, but the main thing is gradient is acceleration, area underneath is displacement. Let's have a look at just a couple of questions. Okay, so we've got a velocity time graph, motion of a cyclist moving along a straight road for 12 seconds. For the first 8 seconds, we've got a constant speed of 6 meters per second, and then decelerates at a constant rate, stopping after a further 4 seconds. Find the displacement from the starting point of the cyclist after this 12-second period. So basically we're finding the total displacement here. Well, that's going to be the total area. Okay. Now we could split up as a rectangle and a triangle, but I think we can probably be a bit better than that and use the area of a trapezium. So this length here is 12. So we've got half times 12 plus this length here is 8 times the height, which is 6. So we're just finding the area under the VT graph to give me displacement. And we get 60 meters. Okay. Part B, work out the rate at which the cyclist decelerates. So we're looking at this slope bit where they're decelerating down to rest. We want to find the gradient of that. So the change is 6 in a time, remember we're just looking at this bit of time here, of 4 seconds. Okay. So 6 over 4, 1.5. Or we should say minus 1.5 meters per second squared, because decelerating. The rate at which they decelerate, so we've got an acceleration of minus 1.5 or a deceleration of just 1.5. Depends what they're asking for. Okay, here's another example. This time we don't have a graph. We're going to have to probably draw our own here. Okay, the particle moves along a straight line. The particle accelerates uniformly from rest to a velocity of 8 meters per second in t seconds. It then travels at a constant velocity of 8 meters per second for 5t seconds and then decelerates uniformly to rest in a further 40 seconds. Okay, so we're definitely going to need a nice graph here. Let's draw a better one than that. Okay. Right, so that's the first question anyway, sketch a velocity time graph. Even if it doesn't say to do that, I think I'd suggest doing that anyway, just to help you solve the question. So it accelerates uniformly from rest. So we're starting at 0 and accelerating uniformly, so it's going to be a straight line. That's the first section. The particle then travels at a constant velocity, so it's going to be a horizontal line for a little bit. And then it decelerates uniformly to rest, so it slows back down to 0. Okay, and this isn't to scale, this is just a sketch for now. I haven't actually put any numbers on there yet. Let's label some of the information. So it goes to a velocity of 8 meters per second in t seconds. Then it travels at a constant velocity of 8 meters per second for 5t seconds. So that means that this would be 6t here, because this gap, it's telling me, is 5t seconds. It then decelerates uniformly to rest in a further 40 seconds. So this bit here is 40. So that means that this final time here would be 6t plus 40. That might be useful to put on there. Okay, well there's our graph, that's done. Find the value of t. Oh, I forgot to read the extra information there. The total displacement is 600 meters. So we know that this total area is 600 meters. So let's try and work it out. So I wonder if we can just do this as one big trapezium. I think we probably can, can't we? So if we consider this as one large trapezium, we know that the area, 600, is half, and we want the long length, which we know is 6t plus 40, plus this other length here, which we know is 5t, times the height, which we know is 8. And now we can just solve this equation. So I've times it by 2 and divided by 8, give me 150 equals 11t plus 40. That's just the bit inside the brackets. Minus 40 divided by 11. So t is equal to 10. There we go, solved it. And that's quite a common strategy in these questions. Is just using facts for areas of shapes. Okay, especially trapeziums come up a lot. And it's much more efficient to use a trapezium than it is a rectangle and a triangle. And I think, yeah, my main tip here would also just be drawing a really clear velocity time graph, even if they don't tell you to. Okay. Exercise 9b is the one to do to practice VT graphs, but I thought I'd pick out question 8 to have a look at. So you might want to do questions 1 to 7 first and come back to this and have a look at question 8, because this is the sort of question that trips people up. So I'm going to go through this now. So it says a motorcyclist M leaves a road junction at time t equals 0. She accelerates from rest at a rate of 3 meters per second squared for 8 seconds and then maintains the velocity she has reached. I'm going to just make some notes of this, I think. So so they leave at time t equals 0, accelerate from rest. So I'm just going to put u, their initial speed, as 0, because it's from rest. The acceleration is 3 meters per second squared, and the time that takes is 8 seconds, and then maintains the velocity she's reached. So basically her graph is going to look like that. A car C leaves the same road at time t equals 0 as well. It accelerates from rest, so we've still got u as 0, up to 30 meters per second. So that's the final speed, is what I mean by u and v. So u is initial, v is final. And t is 20 seconds, and then maintains this speed. So again, their graph is going to look like that. C passes M, so the car passes the motorbike as they both pass a pedestrian. On the same diagram, sketch the velocity time graphs. Okay, well I know they both are going to look like this, but I could do with some more values, and I could do with knowing like how steep the line is as well. That's going to help me sketch it too. So to work out how steep it is, I need the gradient. Well, I've already got the gradient of this one. It's going to be 3 meters per second squared, because remember the gradient of a VT graph is acceleration. I could do with working out the acceleration for this one, just to work out how steep this graph is. Well, the acceleration is the change in velocity over time. So that's going to be 30 divided by 20, which is 1.5 meters per second squared. So I can see that the motorbike's line is going to be much steeper than the car's line. That's quite helpful in sketching it. Okay. Okay. So let's draw the motorbike's one first. So that one's much steeper. Or we could also do with working out what speed it actually reaches, couldn't we? So we know that the acceleration is change in speed over time. So that's going to be v over 8. So the final velocity of the motorbike is going to be 24. Okay. Just because acceleration is change in velocity over time. Change in velocity is just whatever its final velocity is because it started from rest. So the motorbike is very steep, but it actually has a lower top speed. It's flat after that. Okay, now let's do the car in red. So the red is less steep, but it actually reaches a higher top speed. So something like that. Okay, there we go. Let's just label them as well. So the black one was the motorbike, the red one was the car. Okay, let's put on some values as well. So it got up to 30 meters per second in 20 seconds. The motorbike got up to 24 in 8 seconds. So that's a pretty good VT graph. It's fairly accurate. Now, part B, it said C passes M, so they pass each other. They both pass the pedestrian. So basically, they're at the same point at the same time, is what that's trying to say. They go past this particular point in space at the same time. Find the distance of the pedestrian from the road junction. So basically, find out how far away from where they started do they overtake one another. So they're in the same position at the same time. Now, looking at this graph, what most students tend to do is they say, well, where they cross must be this point here, because that's where the graphs intersect. But that's not actually true. All that's happening at that point is their velocities are the same, which might be important, but that's not what the question's asking. The question doesn't say when are they moving at the same speed, it asks when are they in the same position. So it's not that point. What we're looking for is where is the area under these graphs the same? So if I was to shade in this area here, when does that area have exactly the same value as the area under this graph? After how long, basically? That's what we've got to work out. So I'm going to come up with an expression for the area under both of these shapes. Okay, so let's do the car first. And we're going to call the point when they are at the same place. I'm just going to call it capital T. I don't know exactly where that is. Let's put it there. Now the area under the car line, so the red one, well, this first triangle is half of 20 times 30. And then we've got plus this rectangle, which goes from 20 to t, and it's got a height of 30. So that rectangle is 30 times t minus 20. It's got a height of 30, and its length is just whatever this length here is. So that's t minus 20. Okay. Now if we do the same for the motorbike, the triangle at the start is half 24 times 8. And now the rectangle is going to be 24 times this length here, which is t minus 8. Okay, so we've now got an expression for the distance travelled by the car, which is the area under the graph, and the distance travelled by the motorbike, which is the difference travelled, the distance under the graph, or the area under the graph. Okay, and we want to know when are they in the same place at the same time. So we want to know when do they have the same displacement. So I'm just going to set these statements equal to one another. So I've got the car. I'm going to simplify them in a minute, but I'll write them in full for now. Like that. And now it's just about solving this and simplifying it. So I'm going to work out a few of the number bits. So that'll be 300 plus 30t minus 600. That would be 96 plus 24t t minus 192. Okay, so that could be 6t equals 204. So then t is 34 seconds. So what this means is that after 34 seconds, the areas underneath these two graphs are the same. So they would be in the same position after 34 seconds. Now, that's not quite what the question asked. It asked how far. So we've now just got to substitute that into one of our expressions. So I'm going to substitute that into this motorbike one, I think. So that'd be half 24 times 8 plus 24 times t minus 8. So that's going to be 34 minus 8. Just to find out exactly what is the displacement at that point in time. Which gives me 720 meters. Okay, so that's my final answer, is after 720 meters, the car and the motorbike are in the same position. So that's quite a tricky one, but I thought it was worth showing you that one in particular, because one the students always find hard.